These are going to be our notes on what is called the fundamental theorem of calculus. So far, what we have discussed in this course feels like a couple of major topics. That would be derivatives and integrals. Of course, we also talk about limits, but the two big focuses thus far have been derivatives and integrals. We spent the majority of the class so far talking about derivatives. And then we have spent the past few sections talking about this concept of an integral by taking the limit of Riemann sums. So what we'd like to be able to do is have some kind of connection between them. And it turns out the theorem that's going to do that for us is the fundamental theorem of calculus. So the first part of the fundamental theorem of calculus starts with the assumption that we have a continuous function f on an interval from a to b. And then with that assumption, we then define a second function, g, to be g as a function of x, defined to be the integral from a to x on f of t dt. So we can see, because this is function notation, x is the variable in this function g. And notice where x is in regards to this integral. X is the right endpoint of this interval. If we were interpreting this graphically, what we would say is that G describes the area under the curve for a variable right endpoint. In other words, it's the area under a curve where you set the left endpoint and you watch what happens to the accumulated area as that right endpoint changes. So let's see if we can take a look at a graph to kind of further cement and understand what this actually says. So here is a graph. Let this graph represent f of t. This is the continuous function on the interval that we're talking about. And so what we want to talk about is that function, g. What does it mean to have g of 0? So let me write down what g was again. So this is from the previous slide. So g of 0 literally means that you're taking the integral from a left endpoint. Now in this particular case, our left endpoint is showing up here at 0. To a right endpoint of, the input tells us the right endpoint, of 0 on this function f of t dt. So this particular question is actually pretty quick and easy if you take a look at the fact that the left and the right endpoints are both 0, which means the area underneath the curve starting at 0 and ending at 0, yet there's no space, there's no width to that interval, so the actual area is going to end up being 0. Okay, so let's take a look at a slightly more interesting question. Then what would, let's say, g of 4 be, for example? So that would be the integral from our set left endpoint of 0 to the given right endpoint of 4 on f of t dt. Now, if you notice, I have purposely given you a function, f of t. These are lines. I haven't made these curves. So when we talk about the area under this, we're actually looking for the area right up to here, would be our 4. So we're looking for the area up to this part of the graph right here. So it's a little bit hard if you take it as a whole, but if you split this into two separate shapes, the first shape being a triangle and the second shape being a rectangle, the area under this curve is actually pretty straightforward to compute just by looking at them as familiar shapes. So the area of our triangle would be 1/2 the base, the width of that base is 2, times the height, times the height, which is going to be 6. And then the area of the rectangle is the width of the rectangle, which is 2, times the height of the rectangle, which is also 6. So when you're done with that, the area is going to end up being 18. So the integral from 0 to 4 on f of t dt is given as 18. Now compare that to a question like g of 8. Again, that is asking us to find the integral from 0 to 8 on f of t dt. Now, by properties of integrals, we should be able to split that to be the integral from 0 to 4 on f of t dt, plus the integral from 4 to 8 on f of t dt. Okay, so we already know what the integral from 0 to 4 is, and we're going to make use of that. We don't want to double up on our work. So that's going to be 18. And then the integral from 4 to 8. So again, here's our 4, and here's our 8. Okay, so we're actually looking to add to that this area. Oops. And this one, that's supposed to be a straight line. This one's even a little bit easier because it's one single shape. In this case, a triangle. And the calculation for that will be, again, 1/2 base times height, where the base is going to be 4 and the height is going to be 6. So when you take 18 plus that, you're going to end up with 30. So g of 8, which is the integral from 0 to 8 on f of t dt, ends up being 30. So let's take a look at one more. Let's talk about g of 9. I'm going to have to move this one down here. So again, g of 9 is going to be the integral from 0 to 9 on f of t dt. We already found the integral from 0 to 8. That was going to be 30 for us. And we're going to add to that the integral from 8 to 9 on f of t dt. So this is the one thing that's a little bit different. So when you go from 8 to 9, let me change colors here so we can see it a little bit better. That will be here. So it is a triangle. So it is going to be 1/2 base times height. So I'll repeat the 30 from above. The calculation for the area of the triangle is, again, it's 1/2 the base times the height. The base of that triangle is only 1. The height is going to be 2. The interesting thing to keep an eye on, though, is remember this particular triangle, the green one, is below the x-axis, which means its area is considered to be negative. So instead of adding it, in this case, we would actually subtract it. So the integral from 0 to 9, also known as g of 9, is going to be given as 29. So that's this function g of x that we want to talk about in the fundamental theorem of calculus, which I haven't even told you what the theorem says. We just needed to be able to know what they mean by this function g of x. So that's what they're talking about with that. So now let's look at the actual theorem. Once you have the understanding that g of x is represented by an integral, and that f, which is the function that's being integrated, has to be a continuous function, there are actually 3 conclusions that we come to according to the fundamental theorem of calculus. The first is that g of x is also continuous on the interval from a to b. The second one is that g of x is differentiable on the interval from a to b, not including the endpoints. Notice the parentheses instead of the brackets. And those 2 conclusions are great, but the really interesting one is that, okay, now that we know g of x is continuous and differentiable, if we were to take its derivative, what we'd actually end up getting is f of x. Believe it or not, as small and concise as that particular conclusion looks, it's actually a really big deal. Because if we focus on that one and we write that in slightly different notation, here's what we're saying. We're saying that if you take the derivative of g of x, which in Leibniz notation says you're taking dg dx, and if I slightly write that in different notation, that's the derivative with respect to x of g. That's all this says. Remember what g represents. So again, here's our d dx. And this is me rewriting, putting in the integral in place of the g notation. And what we're saying is that when you do that, g prime of x, which is the beginning of the idea, equals f of x, which is the end of the idea. So why are we making such a big deal out of this? What we're saying is that when you take the derivative of an integral, what you're getting is f of x, which is that function right there. Now it is now evaluated at x. It's now evaluated at the right endpoint. But the integral is no longer in place. Notice the integral has completely disappeared. The derivative and the integral have undone each other and left only the function of f evaluated at the input of that function g. In this case, that's x. So what makes that particularly helpful is it allows us to take these derivatives and see very clearly what the results are going to be with actually some pretty minimal effort. And let me bring this back to something you already know. If I ask you, what is the square root of 117 squared? Hopefully you can pretty quickly tell me, yeah, it's 117. Now, did you square 117, find that value, and then take the square root of it? Probably not. You just said, look, the square and the square root undo each other and simply leave you with your input. That's what we just said derivatives and integrals can do for each other. They undo each other. So when you take the derivative of a function with respect to x from a to x on this f of t dt, the derivative and the integral essentially undo each other and leave you with f of x with your function evaluated at that variable, which in this case is x. So let's take a look at a couple examples. So we're going to find the derivative of this function g of x, and notice it's defined in the same way that the fundamental theorem of calculus asked us to define it, right? It's -1 to x on the square root of t squared plus 1 dt. So this square root of t squared plus 1, that is f of t for this specific example. So when we go to take the derivative of it, g prime of x, in other words, we're taking d dx of that integral from -1 to x on the square root of t squared plus 1 dt. The derivative and the integral should undo each other and leave us with f of x. Well, if this is f of t, then f of x is this same function, only everywhere you see t, you write x. So it is simply the square root of x squared plus 1. That's it. That is the derivative of the function. Which is a little weird for us because we're used to, when we take derivatives, we're like, no, we need to use quotient rule or chain rule, or no, in this case, you actually just have to use the fact that the derivative and the integral undo each other and leave you with that original function evaluated at x. Let's look at another one. Find the derivative of g of v equals the integral from v to 0 on sine t dt. Okay, so this one has a couple of slight changes. First of all, I used v instead of x. That shouldn't really change our approach. It just means that my input is no longer x, my input is v instead. No big deal. The one thing that we are going to have to take a little bit more consideration of is that the fact that this is now the integral from a left endpoint of v to a right endpoint of 0. And that means technically this isn't fundamental theorem of calculus worthy yet. Remember, it's the right endpoint that has to vary according to FTOC. That's okay. We have a property that says the integral from a to b on f of x dx equals the negative of the integral from b to a on f of x dx. We covered that in a previous section. So we can absolutely just rewrite g of v as the integral from 0 to v on sine t dt, as long as we put a negative in front of it. Now it's ready for fundamental theorem of calculus. So when we take the derivative, g prime of v, the derivative and the integral are going to undo each other. The negative, which counts as a constant, stays in place. And when we get rid of the derivative and the integral symbol, we're left with sine of the input variable, which in this case is just v. That's it. That's the answer. Let's look at another example. Find the derivative of the function g of x equals the integral from 1 to sine x of the square root of t dt. Okay, so we're back to using x, so we're good there. We also have the right endpoint as the endpoint that is varying, not the left endpoint. What makes this one different is the fact that your right endpoint isn't actually just a variable, it's a function of x. So your input isn't a variable, it's an entire function. I wonder if we have a rule that tells us how to take a derivative when you have a function inside a function, which is essentially what this is, right? It's sine x inside this function g of x. Remember, function in a function, that's composition, which means what derivative rule do we need to use to take this derivative? It's chain rule. So we're going to use chain rule on this one. So what we'll have is g prime of x equals. So what we're going to do is we're going to take the derivative of the outside function, meaning the derivative and the integral are going to cancel each other, and we're going to have the inside function, which is that f of t. So this f of t is the square root of, and then we change the input from t to our input. Don't touch the inside function. So we'll have the outside function is the root, the input is sine x, but now we multiply times the derivative of the inside function. So this derivative is the square root of sine x times cosine x. So the first part of the fundamental theorem of calculus shows us that derivatives and integrals undo each other, which I gotta tell you is very helpful. I would love if there were a way to use that to help us simplify the integration process, because I got to tell you, we've been using this one, right? The limit definition of the integral, that the integral from a to b on f of x dx is equal to the limit as n approaches infinity of the sum from I equals 1 to n on f of x sub I star delta x. And I got to tell you, the algebra on some of these has been relatively challenging. And we've been working with what are considered decently straightforward functions. It's pretty much been all polynomials. It's not like we've asked you to do this with logarithms or something of that nature. So wouldn't it be great if there were a way to use this idea to simplify integration? And it turns out that's what the second part of the fundamental theorem of calculus is going to help us to do. So FTOC, the second part, part 2, uses the idea from the first part that derivatives and integrals undo each other, and kind of brings in another idea that we've already talked about. We know something else that undoes a derivative, and that's antiderivatives. So the idea is if integrals undo derivatives, and antiderivatives undo derivatives, it's not that far a stretch to think that integrals and antiderivatives must be related. They both undo derivatives. So that's exactly what the second part of FTOC is going to talk about. Fundamental theorem of calculus, the second part, says the following. If f is continuous on AB, then the integral from a to b on f of x dx is equal to capital F of b minus capital F of a, where capital F is any antiderivative of f. Remember this from the previous sections? What we mean by that is when you take the derivative of capital F, you get little f. That's what we mean by antiderivatives. So now, when I'm asked to integrate a function from a to b, instead of using the limit definition, if I can come up with an antiderivative of that function instead, what I can do is simply take the antiderivative, plug in b, the antiderivative, plug in a, and take the difference of those two. So let's take a look at how we can use this to help us. So let's look at the integral from 1 to 5 on e to the x dx. Okay? We, in theory, could try to do this using the limit definition, but let's use FTOC Part 2 instead. So remember what it says. What I need to do is identify an antiderivative of e to the x. Well, the good news is this is one of the easiest ones there is. An antiderivative for e to the x is e to the x, because e to the x is the only non-zero function that is its own derivative. Okay, so what that tells me is that this integral should be equal to the antiderivative evaluated at 5 minus the antiderivative evaluated at 1. In other words, it's e to the 5th minus e to the first power, which is of course just e. So it's e to the 5th minus e. That's it. That's all we have to do to be able to integrate this particular function. I do want to make sure to point out that when you're writing answers to things like this where it says evaluate, it is looking for an exact answer. So this would not be something we'd want to put in a calculator and then give it a decimal approximation, right? I mean, you could do that in general, but that's not what an integral is looking for. We're looking for an exact evaluation of it. Let's take a look at another example. If we wanted to integrate 0 to 1 on x squared dx, okay, I believe we've actually done this particular one before. So look at the antiderivative. The antiderivative for x squared, remember we add 1 to the exponent, so we get x to the third power, and then we take 1 over that new power. So the antiderivative of x squared is 1/3 x cubed. And you can again verify that by taking the derivative of the antiderivative, and it should bring you back to the x squared, and it does. So what we're going to do is we're going to take that antiderivative and evaluate it at 1 minus the antiderivative evaluated at 0. Okay, so we're going to take, watch this notation because this is usually what you're going to end up writing. It's 1/3 x cubed. And then I'm going to put a line here, and I'm going to put the 0 and the 1. What this says in notation form is that I have taken the antiderivative. That's where I'm getting the 1/3 x cubed. But this line tells me that I'm going to then evaluate that antiderivative at 1 and 0, and that I have not yet done so. So this is where I would now go, okay, I have 1/3 times 1 cubed minus 1/3 times 0 cubed. And of course, the second term zeroes out, and what I get is 1/3. That is significantly faster than using that limit definition. Another way you could have written this particular problem, you could have left the 1/3 out front and just done 1 cubed minus 0 cubed as well. Remember, with integrals, we can leave the constant sitting out front, or we can bring it through to both terms. Either one's correct. Let's look at one more example. If we want to evaluate the integral from 3 to 6 of dx divided by x. And let me kind of erase this a little bit so we can actually see what we're looking at. All right, so this one, I purposely wrote it just slightly differently than I've written any of these other ones. The dx is in the numerator. This is, of course, the same thing as the integral from 3 to 6 on 1 over x dx. Okay. So this is taking the antiderivative of 1 over x, which is of course x to the negative 1. Remember, x to the negative 1 is the one power on x where you can't just add 1 to get the antiderivative. Because if you did add 1, you would end up with x to the 0, okay, which is not the antiderivative. Hopefully you remember that the antiderivative of 1 over x is the natural log of the absolute value of x. That's its antiderivative. And remember, we're going to evaluate that at a left endpoint of 3 and a right endpoint of 6. And this is the notation that I use to say I haven't actually done that yet. And then we plug it in. When we plug in 6, we get the natural log of the absolute value of 6, which is 6, minus the natural log of the absolute value of 3, which is 3. Again, we're going to leave these answers exact. This is great as a way to write this. You could also, of course, because this is subtraction between two logs, you could use properties of logs and call this the natural log of 6 divided by 3, which is, of course, the natural log of 2. That's not absolutely necessary. These are both going to be exact answers, but just something you can do if you see it in that direction. So Fundamental Theorem of Calculus Part 2 is going to save us a ton of work when it comes to integration. So basically, in plain English, what it is demonstrated for us is that in order to integrate something, we can simply use an antiderivative.